then what it does is it actually push the return address to the stack. Okay, so return address, whenever you actually do a function call, whenever you hit upon like a return, you actually have to come back to the next instruction of the call, right? So that's the return address. So whenever call instruction is invoked, you first put the return address onto the stack, okay? And then you jump to the label, okay? That's what this call instruction does. And the return address is the address of the next instruction right after the call, right? Because that's where your program actually comes back after you're done with executing this call function, right? So that's return address. And there's also return instruction called ret, RET. In this case, RET it does the inverse of like call instruction. So the RET instruction actually pops the return address from the stack and jumps to that like a return address. Okay. So let's take a look how it works. So let's think about this is stack memory, and current value of RSP, like stack pointer is 0x120, meaning that it actually points to, this is top of the stack, right? This is top of the stack. And if you hit upon this call instruction, now actually you hit upon this call, then, call to mult2 function, right? That's the instruction in your code. You hit upon this call instruction, then what happens is you first push the return address, right? So what is the return address in this case? What would be the return address? 549, 그죠? So this one is the return address, right? Because if you come back from the function call, you actually have to come back to 549. So that's the return address. So if you execute this function call, then what happens is, stack actually grows by one quad word like this. And then this return address is stored here, okay? And this stack pointer is updated because now we just push a new, element to the stack. So push the stack pointer is decremented by 8, and also this instruction pointer is updated to jump to the header of the mult2 function, the beginning, like a beginning of the mult2 function, right? So RSP is updated to now point to the return address, and RIP is updated to point to the right? So that's basically what call function do. The call instruction do. And so actually once you move it to the mult2 function, now you start executing this mult2 function, right? So instructions in the mult2. And then eventually you hit upon this return, like a return instruction, right? And what's going to happen? So return is the opposite. You first the return address from the stack, right? You first pop the return address from the stack and jump to that address. So if you actually execute this return like a RETQ, then this return address will be popped, and this RSP will be incremented by 8, right? Because now we popped it, so your stack actually shrink by one element. And this RIP is now updated to the next instruction here. Okay? So that's how this function, how we transfer control between caller and callee functions using call and return pair. So whenever there's a function call, there's a pair of a call and return. Right? So that's how we pass the control between the two functions. And second part is passing data. So how we can pass those arguments. I explained a little bit. We actually pass the argument using RDI and RSI, all these things. But here is actually more like concrete description of how we pass the arguments. So if you see, let's say there are like in theory there are like many like unbounded number of registers, unbounded number of arguments, right? You can pass like as many arguments as you want, right? So for the first 6 arguments, let's say your function actually has, let's say you have foo is the caller and bar is the callee, and let's say this one actually takes like argument 1, argument 2, argument 3, and so on. Let's say it takes argument n, like an n arguments to pass the. then the first six arguments, A1 through A6, will be passed through these registers. Okay? RDI, RSI, RDX, RCX, R8, and R9. This one are, will take value of A1, A2, A3, and up to A6, right? What happens if actually you want to pass more than 6 arguments? So if you want to pass more than 6 arguments, then you actually have to use stack, okay? From the 7th argument, let's say you should have like a 7 or 8 arguments, then you actually first put like a first 6 argument into the registers, a set of registers, and the next, like a following, arguments will be placed on the stack like this before you actually call the function, before you actually do the function call. So it's like a caller's responsibility to set up all this like a data before actually you invoke the call instruction, right? So you actually want to actually get this like data right before actually you execute this call instruction. So here, this like a stack space is allocated only when it's needed. In other words, only when you actually have more than 7 or more like arguments. Otherwise, you simply use like a registers to pass the value. Also, when you actually return from the function, the convention is you always use RAX register to pass the return value. So whenever you're done with like a function call, you are required to put your like a return value in the RAX register before you invoke the RET instruction. Okay, that's that's convention between caller and callee to receive and send and receive data. Okay. So in this case, whenever whenever we actually already started like this, like a multi-store function, we already received the first 3 arguments, x, y, and z, x, y, and dest in this case, in the 3 registers, RDI, RSI, and RDX. We already received those 3 registers, right? Through using the 3 registers. Then, in order to pass these 2 like a value, like a x and y, because when you actually function call this mod2, you pass the first 2 arguments to the mod2 function, right? But when you actually do this function call, suppose you use the same register, like RDX and RDI and RSI, right? So you can simply just call. You don't have to do anything extra. Just if you call it, then these 2 like XY value will be passed to this callee function using register RDI and RSI. Receive the value in the mod2 function. First it moves the value of A to the RAX register and multiply this value by RSI register, which actually holds the value of B, right? So if you execute this value, the RAX register will hold the multiplier product of the 2. And then you invoke return, then this RAX register, RAX will actually hold the return value. So what happens after you come back from the function, so now you have to execute this part, right, this code. Because you already received the value of T using like RAX register, what you do is you move the value of this T to the memory location pointed to by RBX register. By the way, this RBX register actually holds the value of the RDX register, which is the pointer for dest. Yeah? So this one actually save the value into the dest location, and then you return. Right? So that's how you pass these arguments and also return value from between caller and callee. Any questions about? 네. 그거 좀 이따 설명 다시 할게요. 그냥 짧게 설명하면 RDX가 콜 러 세이브 레지스터라고 하는 건데, 콜러 세이브 레지스터가 뭐냐면 이 콜러 세이브 레지스터는 RDX 레지스터는 이 안에서 이 콜된 펑션 안에서 얘가 템포러리 레지스터를 자유롭게 쓸 수 있는 레지스터예요. 그 말은 무슨 얘 RDX의 값이 이 펑션 콜이 끝나고 난 다음에 브레이크 될 수 있다는 얘기거든요. 브레이크 될 수 있기 때문에 얘가 그러니까 원래 컨벤션으로 봤을 때 이제 그 콜 리 펑션 안에서 맘대로 그냥 템포러리 업데이트 값을 파괴할 수 있는 레지스터가 있고 얘가 값을 보존해야 되는 레지스터가 있어요. 근데 얘는 이제 값을 파괴해도 되는 레지스터이기 때문에 얘를 저장하지 않으면 사실 콜 되는 이 펑션 안에서 얘가 RDX 레지스터를 다른 용도로 막 써도 상관없거든요. 그럼 만약에 돌아왔을 때 얘가 RDX 레지스터의 값이 깨진 거죠. 그럼 거기다 만약에 하려고 그러면은 뭔가 잘못된 연산을 하게 되니까 얘가 먼저 RDX의 값을 콜하기 전에 RDX라는 레지스터에다가 일단은 그 백업을 해놓는데 RDX 레지스터는 얘가 맘대로 바꿀 수 없는 레지스터예요. 콜 펑션 안에서. 그러니까 콜된 펑션 안에서 바꿀 수 없는 레지스터이기 때문에 얘는 그렇게 펑션 콜을 갔다 와도 값이 바뀌지 않는다는 게 개런티가 되는 레지스터니까 얘는 그냥 쓰는 거예요. I'm going to explain more about this call and call saved register. Just I explain the high level in a very high level. So in short, it's because RDX is call loss saved register, and RDX is call Lee saved register. But I'm going to explain the notion in the later slide. Any other questions? Okay. All right. So third mechanism that is necessary is managing local data. So as I said, whenever you actually execute a function, there are some variables declared inside the function, right? And that actually has local scope. That's the reason why those are called local variables. And there must be some, because you only have like a limited number of registers, you cannot really put all the necessary data inside in the register because you only have like 16 registers, right? It's only a very small number. So if you generally have like a more variables than 16. So you actually need like some way to use this like a stack space for allocating your local variables. So that's the next topic we're going to talk about. So there are like a stack-based languages which actually support recursion. Recursion 뭔지 아시죠? Recursive call, 재귀 함수 이런 거 아시죠? So recursive call means a function that can call itself, right? So maybe good example is like a Fibonacci sequence, or what's a good example? Tower of Hanoi, or that's a kind of classic example of function, like a recursive function call. So C, Pascal, Java, major programming languages, they actually support recursive call. And if a language supports like a recursive function call, then the code must be reentrant. So reentrant means that multiple simultaneous instantiation of the single procedure can exist, right? So maybe classic example is something like Fib. You know what is Fibonacci sequence, right? Fibonacci sequence is 1, 1, 2, 3, 5, 8, and so on, right? The relationship is Fn plus 1 equals Fn plus Fn minus 1, something like this, right? It's actually, the next value is just sum of the previous. So one way to implement this function is like a fib n, let's say integer. Fib n, one way to implement this function is if n equals 1, then return 1. Otherwise, 1 or 0. Let's say 1 or 2, then we actually return 0. And if else, we return fib n minus 1 plus fib n minus 2, right? So this is like a simple like a recursive function that actually obtain the value of Fibonacci sequence for the given n, right? Let's say this is n equals 1, n equals 2, n equals 3, 4, 5, 6, something like that, right? So that's a simple like a Fibonacci, like a recursive function call. And in this case, function actually calls itself, right? If you have a function call with like a function like a fib 5, then you actually call like a fib 4 and fib 3. And this one you actually call like a further fib3 and fib2. And this one called it with fib2 and fib1 and so on, right? So this chain of like a function call actually calling itself. So we actually, because at any given time there are like a multiple instantiation of the same like function, like the same procedure. So we actually need some place to store the state of each instantiation, each instance of the function, right? So we actually have to store the arguments, local variables, and return pointer for all of this like active instantiations of the function. So stack is actually used for that purpose. Stack actually so the value, like this storage is necessary only for the duration of the function, right? Duration of the function, like each like instantiation of the function. So from like a called, when you're called and to return. Callee always returns before caller does, right? So this is it fits very nicely to this like a stack structure. So stack actually allocates a frame for each instantiation of the function. Okay, so each stack frame actually store the state. The state means like these things, like arguments and return address and local is a state of the function, and for single procedure instantiation. Okay, so let's take a look at an example. So this one is like call chain example. Let's say we have U function. This is the top level. It's U. And U actually calls like a who inside, and who calls like a mi and mi like 2 times, like twice, and mi function can call like itself. Okay, it's like a recursive, right? So that's like a call like a chain. Then let's say here's an example like a call graph, like a call chain. So U actually calls who here, and who calls like mi twice, like here, this is mi1, and this is mi2. Like it calls like mi number 1 and mi number 2 here. And let's say the first mi calls itself like 2 additional times, okay, like recursively. But maybe second invocation of mi just simply returns. Maybe here is like some like if some condition is satisfied, then return. Then maybe the second invocation actually gets in discard, and then it simply returns without further calling this mi function. That's kind of example scenario. So let's say this is example call chain. This actually invokes this mi function twice, 2 more times before actually it returns. But this like mi function, this instantiation actually simply just return from without further calling this mi function. That's kind of example scenario. Okay. For like this case, we're gonna see how this like a stack frame actually grows as this program executes. So this is what this stack frame looks like. So stack frame, this is previous frame, and this one is like a new like frame for the function being executed, the instantiation being executed. So this like a frame actually holds data such as like a return information, what's the return address for this function, and local storage, like a local those like storage to store like local variables, and temporary space. I'm gonna what are those temporary space? I'm gonna explain you more. And to manage this stack frame, you actually have to execute those like a setup code before you actually call the function. So the setup code includes, for example, if you actually have arguments, like additional like arguments, 7 or more arguments, you actually have to put those like arguments into the stack. And also, if you actually have like some like a caller saved registers, I didn't really explain caller saved registers, but if you actually need to save some register value before you execute the call, then actually you have to save those value before you do. So this is called like all setup code. And when you actually return from this function, you have to execute finish code. So finish code is basically you recover any value that was saved during this for like Callee saved registers, and you actually pop them to recoversion of value, and also basically that's what you need to do, and you also need to pop the return address from the stack to actually come back to the original caller, right? So that's basically what happens before you're executing either like a call instruction or return instruction. So let's take a look, what's actually happening more concretely. So here, you have a U function which actually calls who. So now we actually start from function U. Let's say you're now executing function like a U. By the way, I didn't explain this part. Stack pointer actually points to the top of the stack, like the top of the your stack space, right? And there's like another like a pointer called RBP. This is actually called frame pointer, but it's like optional. It may or it may not be used depending on the compiler. So it's not really a required part, but it's maybe some like compiler generates this frame pointer value as well. So RBP actually points to the bottom of the stack frame. Okay. So in other words, these two pointers actually set the limits of the current like a stack frame. In this case, for like a U. So in this case, P and RSP basically points to the beginning and the end of this function use like a stack frame. Okay. And this is top, and this is bottom. Yes. So let's say you are in the middle of executing U function. So whenever you enter this U function, your like a stack frame for U was already created. So now you actually have like a stack frame for U function, which is shown in yellow color. And let's say now you call who function. You actually reach this point of your function body. And now you call who. Then now like a new function frame is allocated for the who function. And we first execute like this mi function. So now we move on to the mi function. Then the new stack frame is allocated, which is shown in red. So we actually create like a new function stack frame for like mi function. And inside the mi, this one actually calls itself again like mi. Then this one actually there's another stack frame is generated for the same but like a different instantiation of the same function, right? So we actually have second like mi function like a stack frame. Finally, if you have another like mi function call, then we actually have like a third stack frame for mi, like the third instantiation of the mi function. And now let's say you actually return. You return from this like mi function, then you come back like let's say there's return. Then you return from this like a function call. And this like a stack frame is deallocated, meaning that it's like a free, it's a released. It's released to the system. Now, once you actually hit upon return, then this one actually goes away, and the stack frame is recovered. It's like a frame pointer and stack pointers are recovered, and to actually point to the previous instantiation of the mi function. And if it returns again, then now this like a stack frame is deallocated too. And if you return, then this mi stack frame is deallocated. So now we are done with like this part, right? And then we actually have to second instance execute this like a second invocation of the mi function. So in this case, like a new stack frame is allocated in the stack with mi. Then we simply return because there's no further call to mi function. We simply return from this function to come back to the who stack frame. And then we actually return from this who function, and if you actually return from U, then you simply, the stack is come back to the original state. This one is also gone, right? So that's basically how it actually shows the dynamics, how this stack actually grows as you go deeply into the function call, and then how this stack shrinks as you come back from the function call, like a return from the function call. Right? So stack actually is kind of dynamic memory structure. It grows and shrinks, as you make progress in your program using like a function calls. So that's basically it shows the dynamics. Then maybe your natural question is, what are stored in this stack frame? What data is stored? Right? That's the natural question. So here is just like a stack structure, x86 Linux stack frame. So here is a current caller. Let's say in this case, let's say U is the caller, and who is the callee. But note that caller and callee are very relative terms, right? So in other words, this who function is actually callee of function U, right? But it also is caller to function mi, function like function mi, right? So it's both like a caller and callee, and their relationships are very relative, right? So for these two functions, this is caller and this is callee, but in this instance, this is the caller and this is the callee, right? So their roles actually changes depending on the context, depending on where you are in the program, right? So what are stored in the stack frame? So let's think about this. Here is a current stack frame. Let's say you just entered a new let's say you are about to call a new function. Okay, let's think about this. In the previous example, let's say this one was U. Right? Let's say this one is a U, and this is actually a stack frame for who. And let's say you are about to call mi function. You are just before call this mi function. Let's say that's the current program status, right? Then what this a stack frame holds is first you actually have argument build. So argument build means if you actually have to pass more than 7 arguments to the next callee function, then you actually have to put those arguments into a stack, right? So those are extra arguments. It's optional because you only need this part only if you actually have more than 7 or more arguments, right? So this is argument builds. And what about this region? So this region actually holds a local variables if they cannot be kept in registers. As I said, you actually have some arbitrary number of local variables, and you only have some limited number of registers. So in general, these number of registers are too small. This number of registers is too small to fit all your data in the register. So you actually have to. It's very hard to avoid using this stack like a memory. So there are some extra variables that cannot be kept in the register. Then actually you put those values into the stack local variable, and also save the register context. Save the register context is used to save caller, basically backup caller saved registers. Okay, so I'm gonna explain more details about the caller saved and the caller saved. Sorry, I keep postponing this explanation, but so that's actually used for backup, saving this caller saved registers in this stack, and also optional have old RBP. If you use frame pointer RBP, which is actually optional, but if your compiler use it, then you also save the value of old RBP so that whenever you actually return it, you return from function call, you want to recover this old RBP value too, right? Because stack pointer is automatically updated when you actually hit a return instruction, but this RBP must be manually recovered using a move instruction. Okay, so if you actually use RBP, then actually optionally you also store old RBP value so that you can actually recover the RBP value when you actually come back from the return from the function. Okay, and and in the caller stack frame, at the top, we actually have return address, because whenever you're done with the function who, you actually have to come back to the function u, and the return address for within the function u is stored here, at the top of the caller stack frame. So this is actually pushed by call instruction. So once you actually recover this instruction, you come back to somewhere in the u function. Okay, and also there's arguments for this call. This one actually is the same as this part. This is the same, right? That's the contents. That's the contents of this like, stack frame. Okay. So let's take a look at another example, like increment function, how this data is stored in the stack frame. So here's an incremental function. This is another like very like dumb like little function. So it actually takes two arguments as input. The first one is pointer, and second one is value. And what it does is it adds the value to the value stored in pointer, and then update the value at the pointer. Okay, so that's what it does. So it reads the value from the pointer and add like a val to it, and then store this like a sum back to the memory location pointed to by p. And then you actually return the original like a value, the old value of this x at this pointer, the memory location, old value of the memory location at pointer p. So you return that value. So that's what it does. So if you see this function, this function is very simple. It actually first move the value at the pointer to RAX register because it's a return value. You put in the RAX and add this value add this value to RSI register, which actually holds the argument val. So, and then use this. Now this RSI register actually gets the sum of the two, right? It actually holds the sum of these two values, and finally we actually store the value to the memory location pointed to by RDI, like this pointer p, and we do return. This is an increment like function, and let's define another like caller function for this callee. This is like we define another like a function like this. So what it does is call this caller function for INCR function, and we declare two local variables v1 and v2, and v1 is 15,213, and second value is the return value of inc r, and it actually passed the pointer of the first like a v1 variable, and the second constant value is like a 3,000. Okay, so what will it do? It will do, because this one is past the value of this like a pointer. So what this function will do is it actually read the value of 15,213 and add like a 3,000 to it and store the sum back to the location p. So now it will update the value at the location p to 18,213, right? That's what it does. So here, this one is the initial like a stack structure. So currently this one actually points to the return address of the call inc caller of the return address when this call inc r is returning. Okay, so this is the return address for this like call inc r function, and so this one is translated into this assembly code. So if you see, we first allocate this stack space for local variable like v1. So you actually decrement this like a stack pointer by 16 and move this constant value 15,213 into the this part of stack memory. Okay. So initially, this stack structure looks like this, but now, you allocate like a stack memory for this local variable, and we store the value 15,213 to this location, which is this value of v1. Okay. And the question may be, why we actually, decrement 16 instead of 8, right? It's kind of sort of like a detail. I mean, it's not really important thing, but GCC, there is like a calling convention requires that whenever you enter into the new function, then the stack boundary must be aligned to the multiple of 16. That's kind of weird like requirement, but it's part of the spec. So you actually have to abide to it. So whenever you actually, before you enter the new function, your stack address must be aligned to a multiple 16. So that's kind of what spec requires. So that's to comply with the specification. It actually use decrement like 16 instead of 8. But it's kind of really like a GCC, like a compiler detail. So I don't worry too much about it. But conceptually, it's okay to simply just decrement by 8. But to be compliant with specification, it actually decrement 16. So now let's say move on to the second line, long v2. So let's see what happens. So before we actually call the increment function, now we actually have to copy the second argument because it's the second argument. So we always pass the second argument using RSI register, right? So we actually pass this we copy the value of constant 3000 to register ESI. But if you actually use like a move out instruction and use like a ESI register means just simply the lower half of this is like RSI register. And only if you refer to only the lower half of the register, this is like a ESI, right? But if you actually execute this move instruction, the upper 32 bits are automatically put to 0. So even if you execute like a 32-bit move, the upper 32 bits are automatically set to 0. So you don't. In fact, you actually just store the constant of 3000 to the entire 64-bit register. Is what happens. So here, now we actually set the argument, and we also set the first argument to the pointer to the V1. So this value is the pointer to V1, right? Because our this constant value, V1 value, is stored in the stack, right? And the current stack pointer is RSP, and the stack pointer, the pointer of V1 is RSP plus 8 in this case. So we actually pass this pointer to RDI, and we call the function, right? So you are done. So once you execute this function, you already see the body of the function. So what it does is it reads the value from the pointer and add 3000 to it and store the result back to the location at the V1, the pointer. So here, after you execute this function, this value will be updated to the sum of these two original value, 15,213 plus 3,000, which will be 18,213. Okay, and then you now return. The return value will be actually stored in RAX register. So so because now you get the return value from using RAX register, now you add the return value to the original value V1. You add the two value, the original value and new value, and then put the value into the RAX register. So this one actually sets the return value, which is V1 plus V2 in this case. And also finally, we actually recover the stack, right? Because we use these two quad word for local variable. So we actually have to reclaim it. Deallocate it before you actually return from the function, right? So in this case, we do a deallocate by simply adding this stack point, a 16 to the stack pointer. So in this way, we can, now the stack pointer points to the return address again as an initial state of the stack, right? So now if you execute it, now you come back to the initial recover the original a stack state, as you have seen here, right? So here is an invariant. Whenever you execute a function, if you are done, then you actually come back to you actually preserve the original state of the stack, right? So you actually start executing a function, your new stack frame is grows like this, and then right before you return, you actually come back to the like initial state. When in other words, the stack frame is deallocated, right? So actually, you basically recover the original like initial stack state, stack structure when you are done with the function call like this. That actually this property actually holds for all function calls. Okay. And then now you return. So if you actually execute the return instruction, then now this value return address will be popped from memory, and your instruction pointer is value, right? So actually you come back to the sum like a caller of this function, like call instr, maybe main or something, like main is the function, right? Okay. So any questions about this, like how this stack frame grows and and shrinks and allocate and deallocate and so on? Any questions about this example? 네. 네. 아 그러면 엉뚱한 어드레스 띄게 되는 거죠. 그러니까 여기 어떻게 되냐면은 그러면 프로그램이 버그가 되겠죠. 여기 지금 이 상태에서 만약에 그냥 이거를 회복하지 않고 그냥 만약에 리턴을 실행하게 되면 이 unused에 있는 가비지 값을 그냥 리턴 어드레스로 알고 거기로 점프하겠죠. 근데 여기는 아마 가비지 값이 들어있을 테니까 뭐 아마 어떤 로케이션으로 뛰겠죠. 그럼 아마도 프로그램이 결국은 죽겠죠. 아마도. That's fine too. If you actually push the value, it automatically push the. In short, yes. So you can actually using push instruction, you simply put the value and it automatically increment this RSP pointer by 8, right? But in this case, you have to be careful because, because of the requirement. You have to take care about this alignment. If you actually use like a push instruction, it only increment by 8, so maybe it doesn't comply with the spec in this case. But in general, yes, you can actually use push instruction. Any other questions? Finally, we get to the calling conventions, like caller and callee saved registers, because I deferred the discussion so many times in the lecture. So finally, we come back. Okay, we came to the point I can discuss this caller and callee saved registers. So here's like a convention called like a register saving conventions. Okay, so let me tell you what is the problem. What is the problem first? So here, let's say you have u function and who function, and u is the caller and who is the callee, right? Inside the body of the u, who is called. So in the caller, there's caller and callee relationship between the two. So the question is, when you actually call a new function, what registers can be used as temporary storage in the callee function? That's the question. Okay, so let's think about you actually copy the value of constant, 15,213 to RDX register, and let's say you simply add the value to the return value. Then would it be correct? It depends, right? It depends. If this RDX register is not overwritten by the callee function, then you will get the correct result. But if it's overwritten by this callee function, then you'll get the wrong value, right? That's the problem. So there must be some like convention or some agreement between caller and callee, so that callee function, which registers are safe to be used by callee function must be defined clearly. Right? So in this case, what this u function expects is this RDX value, the value of register RDX will be preserved even after, even across the function call. That's what kind of the expectation of the u, which may not be true, because in this case, who function actually overrides the value of the RDX, right? So it will actually break the value. And then if it returns, this one actually will see the garbage value, because which is overwritten by the callee, right? So the contents of register RDX is overwritten by who function, and this could be trouble because in this case, what this function you expect is this value of RDX will be preserved across the function call, right? So there must be some like agreements which registers can be safely used by callee and which register must not be used by callee. Okay, so that's called like a register saving convention. So there are two types of registers. The first one is caller saved registers, and second one is callee saved registers. Okay, so caller saved registers means it's like caller's responsibility to save temporary values in this frame before the call. Okay, in other words, the caller saved register, this means that it's safe for callee to use them as temporary register. Okay, so caller saved register means that it's caller's responsibility. If you really want to preserve the value across the function call, you, caller, must save the value before you the function call, and then once you return from the function call, you have to recover using pop instruction or something. So you actually save your value into your stack frame before you execute the call, and then once you return, you actually recover this like pushed value from the stack. It's like a caller's responsibility. Okay, and in the second case, this is called callee saved registers. So this means callee must preserve. It's not safe for the callee to use this register as temporary. So it's like if you want to use this register for temporary, it's callee's responsibility. Before you use it, you actually save it to the stack, and then you actually have to recover the value to the register before return to the caller. So in that way, caller sees the original value across the function call, right? So in this case, callee. So if you like same thing, it's not safe. It's not safe for the same thing, callee to use them as temporary storage. Okay. So callee must save these temporary values in the frame before using, and callee restores them before returning to the caller. Okay. So for like these callee saved registers, the caller can expect, this value of register will be preserved across the function call. You don't have to back it up. It's like if this value will be overwritten, callee must save this original value first, and then you restore the value before return to the caller. So from caller's perspective, you don't have to worry about this breaking this value because this callee will take care of this backup and restore before you return from the function. Okay. So in like x86 64 register, so return value register, this is caller saved, return value, this is caller saved register, and arguments register is also caller saved, and R10 and R11 are caller saved registers. So all these like registers are caller saved, meaning that it's safe for callee. It's okay to callee to break this value. It's okay to use this value, these registers in the callee function without worrying about this breaking the program. In contrast, like RBX, R12 through 14, RBP, RSP, these like those registers are callee saved register. Okay, so in other words, these caller expect those registers will not be broken across function call. Okay, so if you really want to use this register, the callee, if the callee really wants to use this register, you must, back up the original value into your stack frame, and then restore the value before you return from the function. This is the callee's responsibility. Okay, so RBX, R12, R13, R14, RBP, they are all like callee saved, and RSP is kind of special register, so it's like because RSP is kind of automatically, in many cases, automatically is adjust, like push and pop instruction or call return. So it's kind of special register. And RBP is also like generally call resaved, but they may or may not be used as like a stack frame, as frame pointer. If it's not used as stack frame pointer, then you can use it as like a general like call resaved register. Okay. Everyone understand the notion of caller and call resaved register? Okay. So it's like a convention between caller function and call function, which register will preserve their value before and after call, and which value don't have to preserve their values before and after the call. Okay. So then now we can understand what this thing happens here. So I mean, so caller. Let's see like caller and call resaved register here. So here, again we see the same like call increment 2 like function like, and then before we start the function, we first actually push the value of RBX, right? This one is like a backup. And note that there's a corresponding pop instruction here, like this. So if you see this, we first you keep the original value of our stack, and before we return, we recover the original value, right? So that means, from this caller's perspective, there's another like a function like a main. Let's say main function actually calls this like call incr2. This main function's perspective, the value of like RBX register doesn't change across the function call, right? Because already it's saved here and it's recovered before you return. So this one actually see the RBP value here at this point of program will be same as RBP value here, right? Before and after the function call, the value of RBP is the same, because it's actually pushed here at the beginning of the function and it's popped before returning. So this original value in RBP right before the function call will be preserved right after the function call. So if you see this, we actually push the RBX register, the saved value of RBX, and we also we also like decrement this stack pointer by 16. And before we return, we simply add like 16 to the stack pointer. So now actually, after you're executing this thing, you will actually, now stack pointer will point like this once you execute this thing. And then you execute pop, then the original value of RBX will be recovered. Okay. So actually, let's go back to our original example in one of the first example in slide 3 or 4. Not here. I didn't explain this part very well, but now I'm going to re-explain why we need to do this. In slide like 8. So the question is why we need to save the value of RBX. So of course you know that RBX is caller saved register, call resaved register. Meaning that the value of this RBX must be same before and after this function call, right? So we first save the value of RBX here. So we actually save the value of RBX, and which will be returned right before the function call, right before the return, right? So we first save the value of RBX, and we use the RBX as temporary storage here, right? So we use the RBX as temporary storage. Because RBX is like called resaved register, we know that this value of RBX and this value of RBX will be always the same. because it's Cole-Lee saved register. So it's Cole-Lee's responsibility to not break the original value, right? So we know that if you actually put this value into RBX, we know that, oh, this value of RBX will be preserved across this function call. These two values will be exactly the same, right? But this property does not guaranteed for this RDX register. The RDX register actually is called LUR saved register, meaning that it's okay for Cole-Lee to break the value, right? So if you don't do this, if you basically don't move this Cole-Lee saved register, the value in the Cole-Lee saved register in the Cole-Lee saved register, this value can break across the function call, right? So actually, in this case, fortunately this is not broken, but in general, it's okay. Any function is okay to it's okay for the Cole-Lee function to break the value here because this is the LUR saved register, right? So in this case, it moves the value to Cole-Lee saved register and then use the value after the function call. That's the reason why we actually move this value of RDX to RBX. Although in this specific case, this register is not RDX register is not really used inside the body of the function, but in general, it can be right? Okay, let's move on. All right. By the way, any questions about this Cole-Lee and Cole-Lee saved register conventions? Nope. Okay. By the way, how many of you actually started this bomb lab? Any problems with the bomb lab? I mean, so far? Not many people have started, I guess. That's the reason. Okay, so if you have any problem, any trouble, please let us know, TAs or myself. By the way, TA, what do you want to go over like tomorrow, like the recitation? What's the topic? Okay. I think it may be good to cover some materials that'll be helpful for homework number 2. Maybe. I think I strongly recommend to use GDB because GDB is a very useful tool for debugging, not just for this course, for like your future projects. I strongly recommend you get used to using GDB. It's a very useful tool. You actually have to use it for this homework. All right. So let's think about how this is like a recursive function call works. By the way, how many slides we have? I think it's be a little bit too tight to cover all these things in like 4 minutes. So I think I'm gonna actually stop here today. I'm gonna cover the rest of the recursive function call parts like next Tuesday. So if you have any questions or